shear force and bending moment diagrams for a simply supported beam carrying a uniformly distributed load. Here RA is equal to reaction at A and RB is equal to reaction at B. RA is equal to RB is equal to WL by 2. Fx is equal to RA minus W into X is equal to plus WL by 2 minus W into X. At A, X is equal to 0. Then W into L by 2 minus W into 0 by 2 is equal to plus WL by 2. FB at B, X is equal to L. FB is equal to W into L by 2 minus W into L is equal to minus W into L by 2. At C, X is equal to L by 2. FC is equal to plus W into L by 2 minus W into L by 2, which is equal to 0. Mx is equal to RA into X minus W into X into X by 2. Yx by 2. Yx by 2 here. For example, here the point from here, for example from here it is x by 2, the center point is equal to WL by 2 into X minus WX square by 2. MA is equal to W into L into 0 by 2 minus W into 0 by 2 is equal to 0. At B, X is equal to L. MB is equal to W into L by 2 into L minus W L square by 2, which is equal to 0. At C, X is equal to L by 2. W into L by 2 into L by 2 minus W by 2 into L by 2 whole square is equal to W L square by 4 minus W L square by 8 is equal to plus W L square by 8. Here, shear force and bending moment diagrams for simply supported beam carrying uniform varying load from 0 at each end to W per unit load at the center. Here, for example, here is the diagram. Total load on the beam is equal to area of the load diagram ABO is equal to AB into CO divided by 2 is equal to L into W by 2 or W into L by 2. RA is equal to RB is equal to half total load is equal to half into W into L by 2, which is equal to WL by 4. Consider any section X between A and C at a distance X from end A. The rate of loading at X, capital X, is equal to vertical distance xt in the load diagram is equal to x over L by 2 into W, since CO by L by 2 is equal to xt over small x. Therefore, st is equal to small x into CO divided by L by 2 is equal to 2x into W by L, which is equal to 2W into X by L. Now load on the length AX of the beam is equal to area of the load diagram AXT is equal to small x into capital X D by 2 is equal to small x into 2W into X by L by 2, which is equal to W by L into X square. Now shear force at X is given by Fx is equal to RA minus load on length AX, capital AX, is equal to W into L by 4 minus W X square by L, since as it is given, which is equal to small x into capital XT by 2 is equal to small x into 2W L into X by 2, which is equal to W I L into X square. Since it is given, then W into L by 4 and W X square by 4. At AX is equal to 0, then W into L by 4 minus W into 0 by L is equal to W into L by 4. At CX is equal to L by 2, which is equals to W into L by 4 minus WL into L by 2 whole square is equal to WL by 4 minus WL by 4, which is equal to 0. The shear force at B is equal to minus RB. is equals to minus W L by 4 shear force diagram at RB is equal to RB is equal to minus WL by 4 since W into L by 4 minus W into, if put X is equal to L, shear force at B is equal to minus RB, since for example here is the RB which is in anti-clockwise direction, that's why here minus RB is equal to minus WL by 4. For bending moment diagram, the bending moment is 0 at A and B. Mx is equal to Ra into x minus load of length Ax into x by 3 is equal to WL by 4 into x minus W x square by L into x by 3. Why here x by 3, small x by 3? For example here plus a WL by 4 into x, WL by 4 into x minus load of length Ax into x by 3. For example here, not for example, वैसे here is the x by 3 distance, center of gravity, load of length Ax into x by 3 which is bending moment at distance x, then we get ml by 4 into x minus WL x square into x by 3 is equal to WL x by 4 minus WL x cube by L. At A x is equal to 0, then mx is equal to 0. At C x is equal to L by 2, then mc is equal to ml by 4 into L by 2 is equal to minus W by 3L into L by 2 whole cube, which is equal to WL square by 8 minus WL square by 24 is equal to 3W into L square minus WL square by 24, which is equal to WL square by 12. The maximum bending moment occurs at the center of the beam where shear force becomes 0 after changing its sign. Therefore maximum bending moment is at C. MC is equal to WL square by 12, but the total load on the beam capital W is equal to WL by 2. Therefore maximum bending moment, but total load on beam W is equal to small w L by 2. Therefore maximum bending moment is equal to small w L by 2 into L by 6. Why L by 6? Why L by 6 here? Hey, note here, the maximum bending moment occurs at the center of the beam where the shear force becomes 0 after changing its sign. The maximum bending moment is at C is equal to MC is equal to W L square by 12, but total load on the beam W is equal to small w L by 2. Therefore maximum bending moment is equal to W L by 2 into L by 3, where L by 3 is the center of gravity. L by 3 is equal to W L square by 6. Here, from here, the distance is center of gravity, L by 3, W L square by 6. Shear force and bending moment diagram for a simply supported beam carrying a uniformly varying load from 0 at one end to W per unit length at the other end. Here it is the load diagram. Here it is 0 at one end, W per unit length at the other end. Here, for example, here taking moments about A, RB into capital L, RB into capital L is equal to W L by 2 into into 2L by 3 Why here 12 by 3? Since total load is equal to WL by 2. WL by 2 is acting at a distance of 2 by 3L from A. RB is equal to RB taking moments about A. RB into L is equal to W into L by 2 is into 2 by 3L. RB, where RB is equal to WL by 3. RA is equal to total load on the beam minus RB is equal to W into L by 2 minus W into L by 3, which is equal to WL by 6. Consider any section capital X at distance small x from the end A. The shear force at capital X is given by Fx is equal to Ra minus total minus load on the length Ax is equal to WL by 6 minus W into X by L into X by 2, which is equal to WL by 6 minus WX square by 2L. So here is the graph of WL by 6 minus WX square by 2L. Here FA is equal to WL by 6 minus W2L into 0 is WL by 6. FB is equal to WL by 6 minus WL square by 2L is equal to WL by 6 minus WL by 2 is equal to minus WL by 3. Somewhere shear force must be 0. Let the shear force be 0 at a distance x. From A, equating shear force to 0 in the given equation. First we get 0 is equal to WL by 6 minus WX square by 2L is x square is equal to WL by 6 into 2L by W is equal to L square by 3. X is equal to L by root 3 is equal to 0.577L. Bending moment diagram. The bending moment is 0 at A and B. The bending moment at section X at distance X from the small x from the end A is given by Mx is equal to Ra into X minus load on the length Ax into X by 3, which is equal to WL by 6 into X minus WX square by 2L into X by 3. WL x by 6 minus WX cube by 6L, length on the load AX. For example, here is the x by 3 छोटा ही रहा है. Maximum bending moment is equal to WL into L by 6 into L by root 3 minus W by 6L into L by root 3 whole square is equal to WL square by 6 root 3 minus WL square by 18 root 3 is equal to 3 WL square minus WL square by 18 root 3 is equal to WL square by 9 root 3. It is the maximum bending moment which is WL square by 9 root 3. It is the maximum bending moment which is WL square by 9 root 3. It is the maximum bending moment which is WL square by 9 root 3. Shear force and bending moment diagrams for overhanging beams. Point of contraflexure. It is a point where the bending moment is 0 after changing its sign from positive to negative or vice versa. First, calculate the reactions RA and RB. Take a moment of all the forces about A. We get RB into 4 is equal to 2 into 6 into 6 by 2, which is equal to 36. Then RB is equal to 36 by 4 is equal to 9 kN. R is equal to total load minus RB is equal to 2 into 6 minus 9 is equal to 3 kN. Shear force at A is equal to plus RA is equal to 3 kN. FA is equal to RA minus 2x. At A, x is equal to 0, hence FA is equal to 3 kN. At B, x is equal to 4, hence FB is equal to 3 minus 2 into 4. The shear force varies according to straight line law between A and B. The shear force is positive, whereas at B the shear force is negative. Between A and B, somewhere shear force is 0. The point where shear force is 0 is obtained by substituting fx equals 0 in the equation. 0 is equal to 3 minus 2x. Then x is equal to 3 by 2 is equal to 1.5 meter. Hence shear force is 0 at a distance of 1.5 meter from A, or shear force is 0 at the point D. The shear force at any section between B and C at a distance x from A is given by fx is equal to plus RA minus 4 into 2 plus RB minus x minus 4. Here, for example, not for example, like here it is 3 x, it is like x, then it is x minus 4. Then minus x minus 4 into 2 which is equal to 3 minus 8 plus 9 minus 2x minus 4, 4 minus 2x minus 4. At B, x is equal to 4 meter, hence FB is equal to 4 minus 2 into 4 minus 4 is equal to 4 plus 4 kN. C, x is equal to 6 meter. Then FC is equal to 4 minus 2 into 6 minus 4 is equal to 0 at x is equal to 6 meter. Between B and C also shear force varies by straight line. At B shear force is plus 4 kN, and at C shear force is 0. The bending moment diagram. Bending moment at A is 0. The bending moment at any section between A and B at a distance x is given by mx is equal to RA into x minus 2 into x by 2. 2 into x by 2 is equal to 3x minus x square. At A, x is equal to 0, then MA is equal to 0. At B, x is equal to 4, hence MB is equal to 3 into 4 minus 4 square is equal to minus 4 kN meter. Maximum bending moment occurs at D, where shear force is 0 after changing its sign. At D, x is equal to 1.5, hence MD is equal to 3 into 1.5 minus 1.5 is equal to 4.5. At D, x is equal to 1.5, hence MD is equal to 3 into 1.5. At D, x is equal to 1.5, hence MD is equal to 3 into 1.5 minus 1.5, which is equal to 4.5 minus 2.25 is equal to 2.25 kN meter. The bending moment between A and B varies according to the parabolic law. The bending moment at any section between B and C at distance x is given by mx is equal to RA into x minus 2 into x by 2 plus RB into x minus 4. For example, here x minus 4. Then MB is equal to 3x minus x square plus 9x minus 4. At x is equal to 4, mb is equal to 3 into 4 minus 4 square plus 4 into minus 4 kN of meter. Here at mb is the, at x is equal to 4, the answer came is minus 4 kN meter. At here is the minus, at c x is equal to 6, mc is equal to 3 into 6 minus 6 square plus 9 into 6 minus 4 is equal to 18 minus 36 plus 18, which is equal to 0. The answer came is 0. Here the answer came is, for example, between a and b, 3x minus x square. The answer came is 2.25 kN meter. 2.25 kN meter. The relationship between load, shear force and bending moment is F is equal to dm by dx. F is equal to dm by dx.